Hello. Today we're going to start our next topic, our next chapter, which is systems of linear equations. So we've spent a lot of time working with linear equations, graphing them, writing the equations themselves. Today we're going to sort of expand that base. We're going to look at more than one linear equation at a time. We're going to stick with solving two linear equations at the same time. So think about solving, when I say solve, that's why we graph them, because that line represents the infinite number of solutions to that particular equation. So now we're going to look at two sets of infinite solutions, two lines. And what we will be looking for every time is that point of intersection. So, write this one down. The solution to a system of linear equations is that point of intersection. I'm going to ask you that on a quiz. Tell me, what is the solution to a linear system? It is that point of intersection. So we will be looking for that point. And we're going to look at a couple, three ways to get to that point. But first we'll start out with sort of an easier question. I may give you a linear system. It's going to look like this. So here's a linear equation and here's a linear equation. And what I'm looking for is that point of intersection. I may give you a point, the x and the y coordinates, and ask you, is it the solution? So taking a look at this particular system, I may ask you, is the point 3, -2 the solution, or a solution to that system? So a couple ways we could go about this, but the easiest way to answer a question like that is what? Plug those numbers in, right? Because I'm asking you, is this point on this line and on this line? Okay, so it has to work for both lines. So we're going to plug these two numbers into both equations, do some easy arithmetic, and then we will say what? Yes, it works, or no, it doesn't. In order to say yes, it has to work in both equations, not just one of them. So let's check it out in the first equation. 2 times 3, and be careful, minus -2. Does that equal 8? So that is 6 plus 2, which is in fact 8. So this point could be found on this line. Now we need to see, can it be found on the second line? So I'm going to plug those numbers in there. 3 plus 3 times -2. Does that equal 4? So 3 minus 6, that is not 4. So the answer to this question is no. How come? Well, yes, it worked here, but no, it doesn't work here. So it's not on this line. So if it's not on this line, then these two lines can't intersect at that point. Okay? So again, if I ask you this question, is a particular point the solution to a system? You will answer me, yes, it is, or no, it's not. How will you find that out? You will take those two numbers and put them in, plug them in. If it works in the first equation, you will go on to the second equation, check it out. If it doesn't work here, then the answer is no, it's not a solution to both of these at the same time. okay? If this point doesn't work in the first equation, you're done, right? Because if it doesn't work in the first one, it doesn't matter if it works in the second one. So if the first equation is a no, then the total answer is a no, okay? All right, so that's one way you might see a question posed as far as a system. What we're going to look at first off is the first method for solving a system. So the first method for solving is graphically. We're going to solve it by graphing each equation and actually naming that point of intersection. So let's start out with this one. All right, review time. How do we graph a linear equation from the equation? Remember, I'm not going to be plugging in numbers. I have enough information right here to graph it, as long as I put each one in slope-intercept form. Slope-intercept form is y equals mx plus b. So let's take this first equation. To put this in slope-intercept form, we would add x to both sides. And the good news here is what? We already have a coefficient of 1. We don't have to divide it by anything. That equation is good to go. Let's get this one in slope-intercept form. What do I have to do? I have to subtract this x. All right. And again, on this one, coefficient of 1 already. We don't have to divide by anything. All right. Now we're ready to graph each of these equations. Now, when we were graphing single linear equations, we were pretty general about it. We weren't precise. We didn't have to be precise as long as it was rising, if the slope was positive, as long as the y-intercept was identified correctly, we were good. Here's the problem with systems graphically. You have to be more precise, which is difficult, okay? You have to be more precise because we are going to try and name that point of intersection, okay? So, recommendation, get some graph paper, all right? That is the best way to proceed with these problems. All right, here I go. First equation. Remember, how do we graph from the equation? We start with the y-intercept. That is 0, 1. Then we come over to the slope or the coefficient on x. So this has a slope of 1, so that tells me what? Up 1 over 1. Okay, so there's my first. I'm going to connect these dots. This is the one section that I have a lot of difficulty with because I have trouble drawing that straight line, but we'll do the best we can. Easier on graph paper. Second equation, same process, right? 0, 3, start there. Now, this has a slope of what? -1. So that says move down 1 and over 1. And there are my two lines, okay? Clearly we have a point of intersection right here, okay? Let's name that. So that is over 1, up 2. So this point, 1, 2, is the solution to both of these equations at the same time. It's the only pair of numbers, clearly, that's on this line and that's on this line. So that is the solution. Now, I'm not going to take my drawing, I'm going to check myself because, again, my drawings are not that great. So I have to check this. How do I check this? I take those two numbers. I always go back to the originals. Okay, that way if I made a mistake from here to here, it won't work in the originals. So I'm going to test these two numbers, this x and this y, in both of these equations. And it's pretty quick, especially this system. Numbers are small. Here we go. This first equation says take the opposite of x. So that will be -1 plus 2. Is that equal to 1? Yes. So it works there. Real quick here, check it out. 1 plus 2 is, of course, 3. So that quick check tells me what? Tells me, first of all, I put them in slope-intercept correctly. I took that information, my graph is correct, and I have correctly identified that point. Okay. So we will be looking for that point of intersection as we graph these linear equations. Let's take another one. Okay, x plus 2y equals -3, x minus y equals -6. So we're going to change each one to slope-intercept form. First one, subtract that x. And then, because we do have a coefficient, we have to divide every term by 2. I'm dividing -1 by 2 and -3 by 2. Okay, this one might be kind of hard to graph. Let's see what happens. Let's get this one in slope-intercept form. We have to subtract that x. And then we have to divide by the negative. Okay. So step 1, take each equation, get it in slope-intercept form. Step 2, graph each one. First equation, 0, -3/2. Again, improper fraction, let's change it to a mixed number. -1.5. So where is that? Down 1 and then halfway. Okay, now we look to this coefficient. So that tells me what? From here, I'm going to move down 1 and over 2. All right, so there's my line. I'm trying to connect those dots. All right, hey, visually, my line is falling. I knew it would be because I had a negative slope, so I make sure I do that mental check before I go on. So far I'm okay. Let's take a look at this one. Easier. We start at 0, 6. And we have a slope of 1, so that says what? Move up 1 and over 1. Okay. All right, let's identify this point of intersection. Negative. Okay, on my graph, it looks like -5, 2. But I'm not going to take that for granted. I'm going to check it. Okay, so if I put in -5 and 2, -5 plus 4 is -1, not -3. So this is the issue that we may run into, where our picture's not perfect, and so we have to sort of maybe play around with the numbers a little bit. Okay, so -5, 2 didn't work. All right, maybe it should be a little bit lower. Maybe it should be, maybe this line wasn't as low as I could have gone. Maybe it should be -5, 1. I would also, if that doesn't work, I would check negative 5, 3. Okay, so that's how you're going to, you may have to spend a little more time, check your numbers. Doesn't work, but we're close. Clearly, we're over here somewhere, okay? So you might have to change things around and check it out. So here I go, negative 5 plus 2 times 1. So that's negative 5 plus 2. Yay. That is, in fact, negative 3. All right? Check it out here. Negative 5 minus 1 is negative 6. Okay, so my first thought, negative 5, 2, I wasn't quite there. Right? I had to adjust and see if I could find the pair of numbers because my lines are not perfect. Okay? So the answer to this system is the point negative 5, 1. Okay. All right, so there's the process. I want you to think about, maybe there are situations where I don't have to graph them in order to know what is the solution. Here's what I mean. Here's my system. Okay, I'm going to take each one and put it in slope-intercept form. I have to subtract 2x. I have to subtract 2x. Okay, take a look at these two lines. You can graph them both. Well, let's go ahead and do it. We start at 0, 3, down 2 over 1. Second line, start at 0, 5, down 2 over 1. Again, my picture's not that perfect, but it tells me something. I'm thinking, are these two lines even going to have a point of intersection? All right. And then if I look at the equation, I know that they are never going to intersect. How do I know this? I know this because the slopes are the same. Remember, parallel lines have the same slope. In fact, parallel lines have the same slope and they must have different y-intercepts. Because what if they don't have different intercepts? Then they're the same line, right? So, same slope, different b. That tells me they're parallel. That tells me they will never intersect. And so, even without graphing it, just by looking at the equation, I can conclude that there is no solution to this system because they are parallel lines. So that's one case of I didn't really have to graph it. I could have made my conclusion just by looking at the equations. Okay, here's a system. In this first little equation, we actually have to do a little work. We have to distribute and then see if it's going to be in slope-intercept form. So if I distribute that, I get 2x plus 2 is equal to y. Hey, I know it's reversed, but we do have y by itself. So that is in slope-intercept form. I can flip it around. It's the same as y equals 2x plus 2. All right, let's get this one in slope-intercept form. We're going to add 2x to both sides. what do we see now? After we did that little bit of work rearranging things, it didn't start out looking this way, but after we did that work, we find what? They're exactly the same. They're exactly the same. If I were to graph these two equations, I would be graphing one on top of the other. Where do they intersect? They intersect everywhere. And so the answer to this is infinite. The solutions are infinite. Once again, I can make that conclusion by looking at the equations, because the slopes are the same and so are the y-intercepts. So this is these were two versions of the same equation. So the answers are infinite. Okay? All right. Graphing systems. We're going to do our best to graph it as accurately as possible, both of them, and then name that point of intersection.